today. So as you can see, this is waiting for Godot, which is how I feel like while I wait for a neutron star merger from LIGO right now. But it's okay. We just wait, and it's gonna be great. So what I wanted to do here with you is to give you a little bit of a feeling and the flavor of all the different transients we try to go after, and the type of physics that we're trying to constrain. So it's gonna a little bit of a tour across the many different transients that I like studying. And the broader context is that studying transient is important for many different reasons that go from cosmology to the chemical enrichment of the universe, feedback to galaxies, and of course, a part that I really, really like is that our transients are almost always connected to compact objects like neutron star and black holes, which we can now study even outside the electromagnetic world. So if I have to think about what are the key open questions in the field of transient astronomy, here they are. We know that things can explode in the sky, but we're still very bad in understanding what type of star gives you that particular type of transient. And we are equally bad in being able observationally to tell you if what is formed is a black hole or a neutron star, let alone what are the properties of that new object. What we do know for sure is that sometimes these compact objects are able to stay together until the end, and sometimes they merge on relevant timescales for us, and they can produce some fantastic electromagnetic transients in our beautiful kilonovae. So if I have to spell out the questions, here they are. They are, if you want, the most natural question you can think of. So what happens in the years before the explosion, and also what type of stars explode like what are the properties of the remnants, and what are the properties of the counterparts of these mergers. So for this talk today, I will actually not touch upon the gravitational wave follow-up part, mostly because since the start of the new LIGO season, we just had one neutron star bearing merger that was declared, and we got very excited. It was right after the start of 04, but we didn't find anything, and after that, there has not been any neutron star merger. But I believe in statistics, and hopefully that will happen in all of them will be in the second half of 04. I wanted to advertise just one thing though, where I'm spending a lot of time in trying to organize the efforts with the Rubin LSST to use target of opportunities, so interrupting the main LSST survey, and use these observations to actually monitor and find these EM counterparts. There's gonna be the first of two probably workshops is gonna happen in March at UC Berkeley. The announcement is gonna go out probably in the next week or so. So just keep an eye if you're interested in having a say in what will be the strategy for follow-up with LSST. But that's all I'm gonna say about GW follow-up. If you're interested and wanna know more, please come and talk to me or email me. I'll be very happy to tell you more about what we've been doing. So another way to think about those open questions as an observer, I always think about how I can map those open questions into pieces of a parameter space that I can try and go and investigate. And here I'm trying to name the pieces of a parameter space of luminosity versus time scales, where I think there is a lot of space for discoveries in the next few years. And this is the part, this pre-supernova, pre-explosion life of stars is a part that, in my opinion, will be extremely open for discoveries at the time of LSST. I'm gonna talk a little bit more about what we have learned in the last 10 years and why LSST is gonna be the revolution, in my opinion. And then the other part of parameter space that I find extremely interesting is very late time studies. So we have been doing kind of a good job in mapping the central part of our transients, because that's a part where they are the most luminous. But as you can see, we still have a lot to do either before or after. And the other piece that is very, very exciting right now has to do with the very fast evolving transients. And again, it's because the part of parameter space that we have not been able to mine as effectively, as efficiently, just because it's technically harder. And so these are the three areas where I think there will be a lot of discoveries in the next years. Of course, there is another axis that I start getting more and more excited about, which is what I refer to as inverting the trigger. So classically, the time domain astronomer gets their triggers from the optical sky, with some notable exceptions like gamma ray bursts, where instead the trigger comes from gamma rays. Fast radio bursts, trigger comes from radio. But for your average supernova person, the trigger comes from the optical skies. And I'm very excited right now about the possibility, the opportunity to actually use other wavelengths to actually tell optical astronomers to go and find a supernova. And specifically, the radio axis is becoming more and more interesting, and it will be in the next decade or so. I forgot to tell you, but if you want to ask me questions, please do so and interrupt me. I'll be very, very excited to have a conversation instead of just giving you a lot of information that I think is exciting. But as my students tell me, I'm not representative of human nature or humankind. So please tell me what you want to hear from me instead. Okay, so how do we play the game on a day-to-day life as time domain astronomers, time domain observers? So we typically have a discovery engine of different sorts. We're going to discuss about what this discovery engine is that tells us that something exciting is happening somewhere in some parts of the sky. And then if it passes some threshold of how interesting, some minimum threshold of this is interesting or not, it gets passed on to a follow-up team. And we typically have many, many programs approved at any single time. So right now, my team has 35-ish approved proposals. So if we are lucky and the universe produces a transient that falls into one of the categories that we could predict, then it's easy. We just tell all of these facilities, hey, please get on target for me. Many cases, instead, the universe is way more creative than we are, and so we have to write proposals on the spot. But the way you play the game is we go from potentially interesting target into let me get observations across the spectrum. So what is this discovery engine? So classically, that has always been a wide field optical survey. And only recently, let's say in the last 10 years or so, we actually had to couple that with some form of AI. Just because there are too many things flickering in the night for actually me going there and look at each of them. So there is no survey that is operating without some sort of AI right now. And then sources of triggers can be your gravitational wave sky. I'm very excited about the radio millimeter sky and the UV sky. I also think is going to be extremely exciting going forward. So if one of those gives us an interesting trigger, then we trigger all of our programs in other parts of the sky. There is a very interesting sociological aspect that if you want to ask me about over drinks under the night, about interrupting all of your colleagues and tell them stop and go on target, but that's over drinks. So let's go back to the open questions that we have in our field, and let me tell you, so why is this a good time to try and solve these questions? Those are very natural questions. What was before? What was afterwards? So now, why now is good to try and solve these questions? And the reason has to do with the technological revolution. We can actually map the night sky and day sky, if you're a radio astronomer, regularly, and that was enabled by technology. And this is now happening at different parts of the spectrum. We're evolving out of the optical astronomy only. And here I'm emphasizing radio and UV. I also want to advertise that we're starting a new survey that is PI is Peter Nugent at Berkeley Lab. The name is LS4, La Silla's Mid-Southern Survey. It's carried out in the Southern Hemisphere. It's on La Silla. If you remember, if your career started back 20 years ago, you will remember La Silla Quest. That is the same telescope. We are just changing the cameras. You can think about this survey as half of a ZTF, in the sense that our field of view is half of ZTF, but we reach similar depth. The key thing here is that we are in the same sky as LSST. This is my way of solving the need for faster cadence. We have very similar filter as LSST, so that we're trying to minimize the necessity to change, adjust, just convert our observations to LSST-like observations. And I also want to emphasize that this survey has 90%, actually more than that now, of data that are immediately public for everybody. So it's definitely different from other surveys that are around, and we are trying to get on target in spring 2024. Okay, so what have we been doing with this new facilities? So we have been able to map pieces of the parameter space of known transients, but map new pieces of their evolution. And here I'm emphasizing the pre-supernova evolution. The universe God told us very, very, very clearly in 2012 that stars are not quiet before the main explosion. I mean, I think that there were very good reasons to think so even before, but observationally, it was very clear in 2012 with supernova 2009 IP that a supernovae experienced a bunch of outbursts. I'm going to tell you more in just 1 second. So not only we can explore new pieces of the parameter space, but as is always true, when we have a new capability, we always find things that we were not expecting. And among the many things that were found, I want to emphasize superluminous supernovae. So slowly evolving, but extremely luminous supernovae, and the very fast transients, which both of them were not known like 10 years-ish ago. And the reason why now we know very well that both of these things exist has to do with our capabilities to now sample the sky much faster with faster cadence than before. So we go from something like this in terms of cadence when I take observations to something like that. So you understand clearly that's why I'm now sensitive to this fast evolving transients of a few days long, and I wasn't before. But the other part of the answer of finding new things is to look in the right part of the sky. We were relying on amateur astronomers, which are beautiful humans, but we like pretty pictures. So they would take pictures of beautiful galaxies like this. They would not take necessarily pictures of this amazing galaxy at 150 megaparsecs, but that's where weird transients can happen. It turns out that weird transients like superluminous supernovae, they don't like, or F-bots, they don't like the gigantic spirals. They like better this type of environments. So this is important to always remember when we design a survey, that the design of the survey will decide what you can or can't see. So to some extent, we're finding what we're looking for. The other piece of the answer of why now is a good time has to do with the multi-wavelength astrophysics aspect that is very close to my heart. I like the idea of using all the photons that the universe is giving us to try to understand the physics of that particular transient instead of staring at one wavelength. Every piece of the spectrum is going to tell us some different part of the answer. And this is the first step towards what is now reality with multi-messenger astrophysics with gravitational waves and neutrinos. And the first point is giving us discovery power. That's how we know where to point. But that's just the first step, because the real part where we actually make progress is understanding of what the physics that is behind. And the combination of these 2 points is what allows us to make progress in time domain astrophysics right now. And that's why I think is a great field to be in right now. So now let's go back to the picture here. And let me focus on the first half of the problem, which is, what do these stars do before dying? And there are three main ways that, as an observer, we can try and constrain the behavior of the stars. The first is, the most natural thing you can think of is you just stare at that part of the sky and see what happens to the star before the big explosion. And as I was telling you, in 2012, we got a very loud message from the universe that stars are not quiet before exploding. So here you see what happened in 2012 with a supernova explosion, but before, the star was flickering. And here is interesting because the supernova explosion in 2012, but yet the name has a 2009 in it. Why that is so? Because in 2009, some of these outbursts were so loud, so bright, that people thought it was a supernova. And so he got the name of a supernova, but then the star kept flickering around, so clearly it wasn't dead. And so the name cannot be, it's really wrong. It's just not a supernova in 2009, but it was 3 years later. And as always happens in astrophysics and to observers, once you find one, then the game becomes easy. You know what you're looking for. You just need to design an experiment that can find things just what you have seen. And O9IP is what allowed this game to be played. And now outbursts we know are very, very common. But O9IP was good and bad at the same time. And here is why. Because we got very, very lucky and we had HST pre-explosion images taken in 1999. So we could really go there and say, this is the star that is doing all of these outbursts. Great, fantastic. I know what stars is doing that. And it's so luminous that here people don't agree about 60, 70, I don't care. Yeah, question.
Finish the sentence.
Yeah, so people don't agree about the actual mass, but it's so luminous that if you interpret that, and caveat, you interpret that with stellar evolutionary tracks and know nothing about those outbursts, then you would infer this very large mass. Question.
Now my question is, how do we know that it wasn't doing an outburst in 1999?
We don't, and that's part of the problem. I completely agree with you. Yes, that's a huge problem. No, we don't. We don't know that. However, the reaction of the community was, this is very luminous. I saw these eruptions, then maybe those eruptions is something that only happen in the most massive end to the distribution. So it is something interesting, but these are way less than 1% of all stars. At the end of the day, why I would care. And what I would like you to take home from this talk is instead that these eruptions happen across the mass spectrum. Basically, you pick your core collapse supernova. At some point, you will find some eruptions happening. So there is some mechanism, maybe not the same, that is able to produce eruptions in all the stars that explode. So with this goal in mind, to understand how common these eruptions are, we started searching for these eruptions in the most common type of supernova, type 2P supernova. If you had asked me 15 years ago if I would ever have done anything in type 2P supernovae, science would say, no way, no way. They are common, we're well understood, there's nothing to do there. And I was very wrong, very, 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 very wrong. So now I love type 2Ps. So type 2Ps get their name from this plateau. So there it is an optical light curve. They have a plateau. So we call it type 2 because they have hydrogen. And they have a plateau, so P for that. And they are the most common way you can die as a massive star. And they have hydrogen. But they are special because these are one of the type of explosions for which we know the progenitors. So we can play this game of having pre-explosion images just there where those two lines converge, and you look at that afterwards, the star is gone. So clear proof of an explosion. So we know the types of progenitors, and these progenitors are red supergiant stars. So the beauty of type 2Ps is that I know roughly what type of stars are exploding. And people might not agree about exactly what mass is there, but that is a red supergiant star. So for a long while, no type 2b eruption was found. However, people had very good reasons to suspect that some eruptions would happen right before explosion. The reason being this very prominent UV light at early times. So longer lived compared to what you'd expect from shock breakout, and very luminous. So people thought that is most likely suggesting that the shock is not going into the vacuum, but is seeing some mass in the environment, and that allows more efficient conversion of kinetic energy into radiation. However, we were missing the proof that there was some eruption, and that came in very recently. My grad student, Wayne Jacobson Galan, was looking at all the images of all type 2 supernovae in the Young Supernova Experiment Survey. And you can clearly see this is a merger of all the images, pre-explosion images in sponsors. And you can clearly see that there is a source. So the star underwent an eruption. So basically, even the most common type of supernovae, they can also have eruptions before. The reason why, as you might have suspected, the reason why it took for us so long to find the first eruption is just an observational bias, in the sense that they tend to be way less bright. This is actually in luminosity space, way less luminous than the eruptions for other types of supernovae. And so you just need to have a survey that goes deep enough. And that's why I do believe that one of the things that LSSC will do really, really, really well is these type of studies. At the end of LSSC, we're gonna have 10 years of data, so that every single supernova that explodes, you can go and ask yourself, what was the star doing in the last 10 years before explosions? And you get it for free with what I consider a low cadence of the main survey, and nothing to do about it. It's gonna get done for us. And that's why I put here a big part of in terms of discovery potential. The other reason why I like now type 2Ps is because of their very prominent UV brightness. You have a light curve here, and you have here UV, and here is optical. So if you want to know what the stars do at early times, you look at this plot, it should be a no-brainer that using the optical is not the best choice, and that UV is actually the wavelength to use. And UV is also very, very sensitive to how much mass you have in the innermost CSM, innermost medium. So it's gonna tell you a lot about what the star has ejected just before death. So I'm a part of the UVEX team, and what UVEX, which is we are now going through phase A, final selection will be announced probably 1 month or so. And what UVEX will do for the time domain world is to deliver this type of UV spectra at very early times. So first of all, here I plot a spectrum as a function of wavelength. And you can clearly see that if I have to choose between taking an optical spectrum and a UV spectrum, well, the choice should be, give me a UV spectrum. I have way more features that I can use to constrain my parameters. The real issue right now is that what we have right now to get this spectra is HST. And the earliest that we could get on target historically for a supernova is still, I don't have a plot here probably, but this arrow here, which is the first ever UV spectroscopy of supernova, is 87A. We have never got better than 87A. And it has to do with the fact that HST can't repoint fast enough. I have a report of 100 pages from a Space Telescope that explains to me why 48 hours is the limit. And to give you an idea, there's of the timeline. I really like this plot because it gives an idea of how things happen in reality. You can see when things got announced, when they submitted their TOO, and at 2 days, and the first observations happened at 5 days. And this was the record holder until a few months ago, and it was beaten by IXF, but we're still talking about 3.6 days. And that is really long time for if you want to capture really the signature of interaction with a very confined medium. What UVEX will do for us is prompt UV spectroscopy over timescales of hours. So think about that, just like having Swift, but with UV spectroscopy, that we could get UV spectroscopy basically of every supernova we want.
Can I ask a quick question?
Yeah.
So what are the, I mean, how many supernova are you going to be able to identify then to feed to UVEX? Because at what point does it become limited by the discovery time of the supernova? Or are you hoping to discover them in the UV?
Yeah, the game that we're hoping to play, actually I don't have the slide, I thought I had, but it is the synergy with Ultrasat. So Ultrasat will be launched in a few years from now. And what the game we want to play is not only to draw from our own discoveries, because UVEX also has imaging, but to use Ultrasat as well. And so at the end is more of how much time do you want to invest in a supernova than anything. What we committed to in our proposal is to end the first 2 years of the mission with at least 20 core collapse supernovae within 48 hours of explosion. That's what we committed to. I think that it's an easy target to reach 20, and that way more can be done. Yeah. Okay, so the other way you can use to study your medium is very much connected to the UV spectra that I told you about. It has to do with flash spectroscopy. It's a really bad name in the sense that the name is actually wrong, but it's a good tool. And let's just say flash means getting on target fast. So, and let's forget about the physics implication of the name. So, so in this case, you want to get on target fast. Why? Because you have an explosion. This is your medium. It will ionize your medium next to you, and then you're going to recombine. And that time scale is very fast, depends on how dense you are. So if you want to understand what you're made of just next to the explosion, which is a proxy for what the star is made of at the time of explosion, then you need to be extremely fast. So you need to identify your supernova, get on target, and do it multiple times during the same night. And that's what was done for 19 EHK. You can clearly see here is an H alpha line. Just look at the red line to the black one. It goes down over a time scale of 1 night. So if I miss that first night, everything is gone. So technically, this is actually very challenging, but it's very rewarding because it's telling us that that explosion, which is a cosine-rich transient that people thought was connected to white dwarfs, actually had some hydrogen in its surroundings. Yes?
What's the minimum time post supernova can you make the observation?
So it depends how fast we are in understanding that it's a supernova, the source that we're dealing with, and what is your next window availability on your telescope. People was as fast as a few hours after explosion, the CTF team was. Yeah, but you understand it's technically challenging. Even the first step of identification is challenging because typically you have a few shots of fast spectroscopy. So it's always a game of thinking, if I spend my shot on this one and then you fail. Also, it's a game where we fail a lot. Of course, here I'm just showing you the cases where it went well. So there is that game of thinking, I only have 3. If I spend one on this, I'm not really sure. What do I do? Yeah. Yeah, I don't tell you all the times that we failed, but it's large. It's large. But that's how science should be. We fail a lot before we find a result. So not only the supernova had hydrogen close by, but we also got evidence that this supernova was very bright in the X-rays. I also want to emphasize another thing, that we were not planning to detect X-rays for this supernova. The reason why I got X-ray data is because we were interested in the UV, and Swift by design has UV, X-ray, and hard X-rays. So even if I was not even thinking about X-rays, we got X-ray observations. And rule number 0 that I tell to all my students in postdoc is you check your data, no matter if you don't expect anything there. And then we look at it and we have X-rays. Just because the instrument was doing it for us. So we have X-rays, and 10 to the 41 erg per second is extremely luminous for a normal supernova. This is not what we were expecting to find. And then, as always, we found one. It's easy to repeat the experiment. I know that this can be there. It's easy for me to convince others to give me time, and it's easy for me to find it just because I know how it looks. So this brings me to the third way that we have to study this pre-supernova activity, which is why we had those X-rays in the first place, which is this interaction of the shock with the material, the shock itself. And here the concept is absolutely trivial. We have a supernova explosion. It's gonna launch a shock in the environment because the velocity are way, way higher than the sound speed of the CSM. And then this is a very well-known source of particle accelerations, and that leads to Bremsstrahlung for X-rays and synchrotron for radio, for example. So if I do a good job and I monitor my supernova, the X-ray and radio from the supernova, the idea is that I will be able to reconstruct this weird profile just based on the X-ray and radio signature that I see. And the whole thing is particularly beautiful because the shock speeds are very, very large, much larger than the ejection speeds of material before explosion. And that ratio can be 100 very easily. That means that if I'm doing my monitoring for 1 year, I'm looking back in the time before explosion a factor 100. So I can actually know what the star was doing in the last 100 of years. So we're given for free this time machine. That's how I think about supernova shocks, to reconstruct a phase of stellar evolution in the last hundreds of years for which we don't have other probes. You had a question, Jared, or I saw you were like...
Yeah, when you say that you're looking at what the star was doing, you mean you're looking at sort of what stuff the star had ejected.
Corrected.
In the previous 100 years.
Correct. Yeah, correct. Yeah, exactly. Yep. And so we started playing that game, and as every time you start doing something in a more systematic way, you start finding surprises. What you're looking at here is one of my favorite images in the universe, which is a hard X-ray image of a supernova 2014C with NuSTAR. And what you're looking at is the result of this supernova shock interaction. And a NuSTAR was not built to monitor necessarily supernovae. It's something that NuSTAR can do, but was not designed necessarily because the threshold is not good. It's actually kind of shallow. But I remember when I called up Fiona and I was begging her to give me time on NuSTAR. And at the end, she said, okay, as long as they're not gonna contact me again, I'm gonna give you 30 kiloseconds, just do it. And then I was jumping up and down when there was actually a source, and the source was bright for 7 years, which we definitely did not expect. But this is just to say that persistent pays off. Once you really know what you want to do, just keep trying. And here you have a spectra that combines Chandra at low energies and NuSTAR at higher energies. And for every X-ray astronomer, this was the first time I was not dealing with half of the spectrum in my life, because typically you get Chandra data and you're left with half of it and you don't know what's the temperature of that thing. And here, for the first time, I could constrain the temperatures, which is a way that I have to constrain the shock dynamics. So for me, it was like, whew, for the first time, I can do what others do. The other thing that we started doing is more systematic radio follow-ups of supernovae. And here I'm shifting gears entirely. You saw how a supernova looks like in the hard X-rays. This is how supernovae behave in the radio skies instead. And in the radio, it's synchrotron emission. We start off at high frequencies, this bell-shaped spectrum, and then we cascade down as the medium becomes more optically thin to radiation because of the expansion of the shock. So we monitor the evolution of this bell-shaped spectra to understand how fast the shock is and how much and what's the density of the shock. And to our surprise, what we found out is that a number of supernovae, that is at least 10%, that was the constraint that we could put, a number of supernovae that exploded as hydrogen poor. So at the time of explosion, as a progenitor, I've lost all of my hydrogen. But 10% of them showed very weird radial rebrightenings that were coincident with spectra becoming rich of hydrogen. So at some point, that blast wave just met and crashed against a wall of hydrogen, which might be the envelope of the stars. So based on this, and on the beauty of radio follow-ups to supernova, it might sound like it's a no-brainer to just do follow-ups of your supernova in radio and the X-rays. But I want to give you some numbers. So in the optical, we have maybe 70,000. This is a slide that I put together a while ago. We have, let's pick 60,000, so a lower limit of optical supernovae known by humans by now. And in the radio, we have maybe a couple of hundred of supernovae. So you understand there is a mismatch. I'm not going to tell you how many we have in the X-rays because it's very pathetic. So you understand that it's very asymmetric, the situation. And if we think about how many we have actually taken a picture in the radio with very long baseline interferometry, we have 8 supernovae resolved in the radio. So the numbers keep shrinking. And we typically report 8, let's say 10 of supernovae per year. And they are discovered on the order of thousands per year. So clearly there is a mismatch, but it's worse than that. It's worse than that. So not only we just follow up a 10-ish of this 1,000, but in this plot, I just want you to focus on how wide these bands are. Wider means it's my way of quantifying my ignorance about that supernova behavior in radio. So we do a reasonably good job in the first year after explosion of supernova. And then you can see that these bars explode later on. After 1 year, we forget about this supernovae. There is no scientific reason to do so. This is all related to the cycles of proposals. And the cycles of proposals are 1 year long. There was nobody until a few years ago that would have given you a second of time, or radio time, to go on target on a supernova that you have not detected in your first year of observations. Nobody would have allowed you to do that. And things are now changing thanks to VLAS, the VLA Sky Survey. What I want to convince you in the next 10 minutes or so is that this part of the sky, so late time radio observations, has a lot of discovery potential that is almost entirely there for us to untap. So here is what happened with VLAS. So VLAS is the VLA Sky Survey. It mapped the entire northern skies now almost 3 times. They're starting their third epoch is actually out. And it was at the beginning of the pandemic when they released their first chunk of data. And think about from the mindset of a time domain observer, we're used to react fast. And we're used on this burst of adrenaline and to be very, very common. And all of a sudden, a lot of telescopes are silent. And so I had to do something, I had to think about something to do. And VLAS just released the data, but they released not the entire thing. They released the data, but they were not in a good format that it would be easy to use. But so we came up with the idea of actually building a pipeline for radio detection, adapting a pipeline from the optical images. And then we started thinking, well, what if we try to match all of the optical supernovae? Let's try to see if they are radio bright sources or not. And to our own surprise, we started finding a bunch. So here is an image of 04 decay. This was really a supernova in 2004, not like on NIP, it was really 04. And then the image of 2019 of VLAS led to a very, very prominent source. You don't need any fancy like detection algorithm to say, hey, there is a source here, right? And VLAS, for radio standards, VLAS is shallow. 1 millijansky is shallow. And yet we have a source that is screaming out loud, I am there. And not only that, but we start finding others. So we started discovering this population of elderly supernovae, like 10 years plus, that were extremely radio bright. Let me try to make you appreciate in just one slide how why this was not expected. So you have luminosity versus time. And you have your typical supernovae that go up and go down as a result of that bell-shaped spectrum going through your window of observation. So that's what you would expect if the same thing would just keep going. And this is where the Vela supernovae ended up. So up high there. So something weird is happening for this Vela supernovae. So why this is interesting in the first place? The reason is that there is a knowledge gap between, and a sociological gap too, I would say, between the world of supernovae and the world of supernova remnants. And that goes like, let's say, starting from 2 years all the way to hundreds of years. We know very little about what these objects do. And now with those VLAS observations, we can go back all the way to a few decades in time. Our oldest target is a supernova of 1965 in VLAS. So it's kind of an old supernova or a very young supernova remnant, depending on what you like. So the reason why this is interesting, though, scientifically, is because you have many things that might happen here that we just don't know about. And the first thing is that we might produce very radio bright supernovae just because the shock is seeing a wall of material that is crashing against too. So again, it's the same mechanism, just move that shell instead of very, very close by, you move it at farther distances. That is interesting because it will point to some non-standard evolutionary path, especially if you are focusing on a single star evolution. The other thing that can happen that can make that supernova bright is that we know that some supernovae, they can produce relativistic jets like gamma ray bursts. And we know that statistically speaking, there must be jets not pointing at us. That's for sure. But we have yet to find bona fide off-axis jet from a supernova. Yet the deceleration of the jet will make the relativistic beaming become less and less important. And at some point, radiation, even if my jet was pointing there, the radiation will be able to meet an observer line of sight that was 90 degrees for me. So one way to rebrighten supernovae is by having a relativistic jet not pointing at us. And the third reason that I find very, very exciting is that if we are producing some neutron star there, and maybe if we don't have too much ejecta around us, then maybe we can see the emergence of this pulsar wind nebula on short timescales. For all these reasons, this is trying to cover this spiral parameter space is actually extremely exciting. And we actually have a couple of candidates for each of the most interesting part. Most of the supernovae that we have belong to interactors with some weird CSM. And how can you tell what is what here? Sometimes the models are very degenerate when you just think about in terms of fluxes and frequencies. And that's my solution. You take a picture. You take a picture here. I'm using the beautiful sequence of 1993J. You can see this is mapping radio, and you can see how the shock expanded with time. And that's what we're doing for the entire sample of Vela supernovae. And hopefully in 6 months from now, I will be able to tell you which ones are the interactors, which ones are the jets and other stuff like that. But this, I always look at this plot and think like this almost look like magic to me. So I've gone much lower than I thought. I just want to tell you in 5 minutes, I promise, what we are trying to do on the other side of the game. and that has to do with the fast and blue optical transients that, in my opinion, are one of the most interesting transients right now. And this is a place where Anna Ho and Dan Perley within ZTF are really leading the way with fantastic observations. So I'm gonna just tell you in 5 minutes why I think they're cool. And the reason is that I think they might be giving us a window into the compact objects that we have formed. So the long story short is that for your average supernova, even if we have formed something inside the ejecta, for a long time, we will have no information about what this thing is, just because there is all the ejecta around. And all we have to do is to wait for things to become transparent. They become remnants, transparent, we can see what they formed. But one hope is that maybe the universe is nice to us and it might produce things that are very asymmetric, so that maybe I have some paths of least resistance for my photons to get out. And maybe I start off with tiny ejecta mass to start with, and maybe that will allow me to see the emergence of the engine much earlier. And that's what I think might be happening for these fast and blue optical transients. Here's where they live. This is a luminosity versus time scale plot. And let me show you the type 1a stripe that allows us to do cosmology because they behave so regularly. And then you have the super luminous supernova up there, and then your normal type 2p that I didn't like before, and now I like them. And you can see that F-bots are, they populate the whole range of luminosity. And however, the most interesting of these are these guys up here, the luminous F-bot. So now people talk about LF-bot, and that's what they are. The reason why they are interesting is the following. I'm gonna go fast forward, but the reason why they're interesting is fundamentally because of their high luminosity and fast evolution, we know for sure that the usual way that we use to power supernovae, nickel 56, radioactive decay on nickel 56, can't work. The argument being that if I want to reach that luminosity, I need so much nickel mass that the diffusion time scale for my photons to go through is much longer than my rise time. That's why I like them, because they need something different from the average supernova. And then the other thing that make me really deeply love these transients is the following. That so let me give you just 30 seconds of context. These F-bots were first proposed to be something different in a paper by Maria Drought in 2014. So everything I'm telling you has happened in 10 years. For a long while, we could not find anything outside the optical, no counterpart outside the optical. And that always limits our capabilities to say what these things are. Optical traces thermal radiation, and you thermalize things, but also you lose memory effectively of what you were before. So the things changed at the end of 2016 when we found a CSS 161010, that will be the entire telephone number. This was a very short transient in the Catalina survey. There was absolutely no prediction for this thing to produce X-ray or radio, but this was very nearby. It was at 150 megaparsecs, which for this type of transient is around the corner. So what I thought was that I had no idea why I would expect any sort of jetted emission from F-bot at all. And I knew that unless they would produce some sort of very fast outflow, I would not be able to detect them. But I decided to try and get on target with Chandra and VLA, and it took to me 100 days to convince them, but they did. And then when we got on target, I got lucky. And again, I'm not telling you all the 90% of cases where I found nothing. So I'm just telling you the 10% or less that worked. And what we found was very bright radio that is connected to velocities that are 60% the speed of light at 100 days. This is the same as a gamma ray burst like speed. So if you will remember just one thing about these F-bots is that these most luminous F-bots are very luminous X-ray and radio sources, really, really luminous. You can see them all the way to large redshift for supernova world. And they can launch relativistic outflows just like gamma ray bursts, but they're not gamma ray bursts because they have hydrogen in their spectra. So they're just a new beast that can launch relativistic outflows that we had no clue would exist before basically 2016. Yeah, so I'm gonna leave you here with some of my trajectories of the things I would like to do in the future. And as always, my principle, what guides my trajectories is that I wanna go in places of a parameter space that have not been sampled as much and try to see what's there. Thank you so much for your attention, and I'm happy to take questions.
Have some questions, make sure you use the room mic. Yeah, so Marcus.
Yeah, so what's the mean mass of hydrogen contained in these F-bots? I remember CSS and CSS for example, like 0.01 to 0.1.
It's tiny, yeah, and it's very hard actually, to be very honest, it's very hard to go from the hydrogen line to a mass, but it's definitely not much mass. So definitely below 0.1, much smaller than that. I agree with that, yeah. Matthew, and then I get there.
Sorry, Matthew, and then in the back.
I was wondering how far back in time from the supernova can you realistically have detections in the radio? Can you do like 50,000, 100,000 years in supernova, where most binary interactions would probably start occurring?
So it all depends on effectively the ratio between the ejection of that material and the shock velocity. Because how fast is my time machine depends on that. So if you go with a red supergiant, let's give it 10 kilometers per second. And then the shock, let's give it, I don't know, a few thousand kilometers per second. And then that is going to be a factor 10 to the 2, let's say 500 to be, and then multiply times the time of my observations, and that tells you how far back. I would have to do it for a long time, and it's not clear that this will be detectable. But the good news is that there are surveys coming up in the radio, DSA 2000, the SKA, they're all low frequency, which is actually good if you want to play this game because the spectra tend to cascade down. So I think there is hope, but maybe not 10,000.
I mean, just to follow up on that, I mean, at some point though, the earlier ejection would itself slow down, right, and make like a shell.
Yes.
So
you should see the
eventually hit the even if it may not be freely expanding. So you might, that would help you because you could get there faster.
Yeah. Yes. Anything that would stall the other stuff. Right. Yeah.
There's a question there.
Great talk, thank you. I was just curious if your group is interested or excited about using polarimetry or spectral polarimetry, and what parts of this parameter space do you think would be the most useful to contribute to like
to spectral, yeah. No, it's fantastic. It's a fantastic question. So the co-lead of my team is Ryan Tornock, and his thesis was specpol of supernovae. So he would be the right person to ask to. But like for a supernova that I didn't have the time to talk about is 23XF is the closest type 2P in the last 20 years or so. With the group of Alex Filipenko did specpol, and the result is pretty amazing because you can really see the change in polarization properties before, if you want to, as the shock was crossing some heavy material, and then when it emerged, you can clearly see a difference in the geometry. So they are definitely very useful. The part that is difficult is the fact that there are many models that would all give you the same feature. So what we would really need, since we can't deconvolve observations, as Ryan would tell you, is actually having some unique features that would say, if you see this, this is what really means. That's the real problem. We can say 1% asymmetric, but how? Yeah, but absolutely very, very beautiful observations with specpol and findings. So if you're doing that, please keep doing it.
Any other questions? Another one from Marcus.
What sorts of observational constraints could one use to either throw out or lean towards a particular theory for the sources of FBOTs?
Of FBOTs, that's a great question. I'm glad you asked because I've been thinking a lot about it. I was actually also discussing with Brian. So my hypothesis right now is that while a few years ago I was really convinced that these were supernova explosions, right now I'm not anymore convinced that they are. I'm convinced that they harbor a compact object, but I can't tell you if it was born that way, like as a result of supernova explosion, or if it was already there. And Brian has a nice model where pre-existing black hole can actually produce FBOTs. What type of observations? Ideally, we would like to do VLBI of an FBOT. It's like wishful thinking because they're too far away. But one of the findings for the closest FBOT ever is that the UV radiation, after many years, after 5 years, instead of going down, it is plateauing. And this is very reminiscent of what tidal disruption events do. Some tidal disruption events in the lowest mass bin, they have this lingering UV radiation that, in my opinion, is suggestive of some accretion process at place. I would like to know how many of these FBOTs do that. Those are a couple of examples.
Yeah, just to add my 2 cents that I think if we interpret these late HST observations as an accretion disk with some outer edge that we can measure the temperature of, is requiring a very large amount of angular momentum, in the accretion disk currently around the first FBOT. So it's a little more difficult to do that with the core collapse because you can only rotate a star so fast. But if you disrupt a star, or either in a post-common envelope system or in a IMBH disrupting a star, it's a lot easier to make a high momentum disk. So I think that's what the one event, which is at 80 megaparsecs. I guess maybe I'll follow up and ask, what are the prospects for actually doing this? Because we had this very lucky event that was so in our backyard, and then most of them, as you say, are much larger distances. So what are our chances of being able to go sufficiently deep at late times to see the disk?
Yeah, I did numbers, and if everything looks like 18 cow, which was 16 megaparsecs, then we might have a shot with 161010 CSS because it's 150 megaparsecs. Everything else is unfortunately too far to actually even constrain the presence of that plateau. But it's definitely something to do.
So how do we find more nearby ones?
No, that's okay. That's easy. So the way we're finding FBOTs is really not. We're playing the game in the best possible way right now. So in no way I want to be offensive to all of my colleagues playing this game, but we're not doing it in the most intelligent way, in the sense that FBOTs are really, really UV bright. So I go back to UV skies here, and I thought I might have had a slide to give you an idea, but maybe not. I have it. So the FBOTs are very UV bright, and the UV sky is much quieter than the optical sky. So if you could, you would go in the UV skies and then look for UV sources, which would allow us to find FBOTs way more efficiently in the nearby universe. And here we play the game with UVEX, a 5-day survey with UVEX, which is not that big of a field. And right now we have cows are the FBOTs. That's another name of FBOTs in the transient community. Sorry about that. But we have 9 of them right now. And the prediction is in a 5-day survey to go from 6 to 600, the range being our ignorance about the true rate. But that's the way we play the game. Ultrasat, UV, Einstein probe with the X-rays. That's how I'm planning to update my searches.